Hi, everybody, and welcome to today's session of the Spectral Geometry in the Clouds seminar. Today, we are having Yannick Sire from Johns Hopkins University, who will talk to us about spectral analysis of Schrodinger operators. As usual, if you have questions during the talk, you can either unmute yourself or ask the question in chat, and I will relay it. So, Yannick, the floor is yours.
Well, thanks a lot for the invitation. So I'm going to talk about mainly some joint works with Matt Blair from New Mexico and Chris Sogg from Hopkins, related to some cluster estimates or eigenfunctions estimates for Schrodinger operator. So by Schrodinger operator, I mean time independent Schrodinger operator. So basically the framework is the following. Consider closed manifold M, so compact manifold without boundary. And so I denote by minus Laplace G the Laplace Beltrami, and I will be considering Schrodinger type operators of this form, so minus delta plus V. So the potential V will be real valued and singular at critical singularity. So I'm going to explain what this means. And so basically, I will be considering what I want to develop is some harmonic analysis technique for this type of operator. So for instance, like Bognar's, mainly multiplier theorems and eigenfunction estimate. So I want to understand the eigenfunctions, the LP behavior of eigenfunctions of this operator. And if I have time, I will give some results about extensions of this operator to other type of operators where basically you perturb, like this time by a potential singular gain, some powers of the Laplace Beltrami on M, and which these operators here are related to some people call like relativistic operators in all papers in the mathematical physics community. So basically, what I'm going to try to explain how is how to get this type of estimate. So at least like if I'm in a large dimension, bigger than 4, and V is ln over 2. So I will explain this condition. And if I have this number here, then I can have like this type of quasi-mode. So basically I can control the LP norm of U by a lambda for lambda large enough to correct power. And you see like here, I have perturbed my eigenfunction, if you want, by moving the complex plane lambda to lambda plus I, plus this remaining term here. Okay, and U is assumed to be like C infinity, and actually like you can prove that you have this estimate provided P is larger than 2, of course, but small enough. Okay, so the constants here are universal. They depend on the potential, but they do not depend on lambda. Okay, so so here this type of estimate is true only for n bigger or equal to 4. So the dimension bigger or equal to 4. And by what I mentioned before, like what I meant by criticality is that V is in the critical space Ln over 2. Okay, so actually, if you write like an eigenfunction problem, Laplace U plus VU equal to lambda U, or lambda squared U if you want here, then you see that the correct scaling, the critical scaling for V, as far as integrability is concerned, is just like playing with Euler and Sobolev, is ln over 2. Okay, so if you open, for example, a very old result of Koenig-Jerison of unique continuation, you can prove also that this is at least in large dimension, the optimal space for this type of problem. Okay, I mean, like by optimal, I mean like critical for the scale. So what's happening in low dimension? So for dimension n equal to 2 and n equal to 3. Well, then here what we managed to prove is that we have to assume that V is not only in ln over 2, but in the Kato class. So what does it mean? It means that V belongs to the, so here you recognize like locally the fundamental solution of the Laplacian. And here, this is so this integral condition that if you make the soup of on any ball, integrated on any ball of radius r, the soup in X times this fundamental solution, times the potential, and you take the limit, so you are zooming close to the singularity, then this is 0, okay? So Brx here is just a geodesic ball of radius r around the point H. So what can be proven like when in low dimension is that if you are in NL ln over 2 and in the Kato class, so these two classes of function are not like, this is not a trivial assumption, then that they are not embedded one to the other in this low dimension, then you get the usual, you get the same type of estimate, and if furthermore, if you under this assumption, if n is bigger than 4, you have the previous estimate, okay, but up to reminder here, and for all the p's all the way to Placing field. Okay. So you see here, like you have quasi-modes, and well, here there are always an issue when one looks at this type of operator of domains, and so this is like here I take U to be in the domain of the Schrodinger operator, and here R lambda is just the projection operator of the square root of this Schrodinger operator projection over the interval to lambda plus infinity, right? But you see, like here is n, you can take n large enough. So basically, the important thing to remember is that, like, in large dimension, the assumption ln over 2 is enough to get this type of estimate, at least for small p. And in the larger, for larger p or in small dimension, one needs to take, here should be n minus 3. One needs to take V in the Kato class, okay? So the reason why we use the Kato class in low dimension in particular, as far as the quasi-mode is concerned, is because, like, we need to have heat kernel estimates, and in particular, and this cannot be ensured at least when for when the potential of the Schrodinger operator is just ln over 2. So actually, like, whenever, like, you are like in this intersection of these two spaces, if you take an eigenfunction of this, and now I can take n bigger than 2, okay, and sigma p is always this number, then you get that in the sense of distribution, every eigenfunction will satisfy this LP bound. Okay. So this is what we wanted to achieve initially. So this sigma p here is this number here, okay, which is like related to all the numerology I explained before. Okay, so actually, how do you prove that when v is equal to 0 or v is equal to or v is smooth? Well, actually, it's one way to do that. There are many ways now, but one way to do that, so there's so-called like a SOGS estimate, and one way to do that is to use Hadamard parametrics. So basically, one needs to understand an inverse, a formal inverse at least, of this operator, okay? Because this operator for v equal to 0 or v smooth enough, it will not change anything. So, right, this is the operator that I have here when v equal to 0 in my estimate, right, on the right-hand side. So what do I do? What can we do? Well, then, I mean, if you take like this inverse Fourier transform, and you take, which are related to Bessel functions, and you take like Laplace to be like the flat Laplacian, then you can see that for nu equal to 0, this is like fundamental. I mean, this is equal to Dirac, and you can see that you have this recurrence relation. Okay, so this is like a good function to describe somehow like my recursively to describe the eigenfunctions, right? Well, then if you go into coordinates, right, you do like what everybody does, like in this type of pseudo differential calculus, right? You take like a formal expansion of this form, you plug it in there, okay, and then what you can prove that if you choose n large enough, you have this type of bound coming. Okay, so you have constructed an approximate fundamental solution, if you want, of your problem, of your operator here. Okay. Well, then, how do I use? How can I use this? Okay, to control to derive my LP estimate here. Always in the case, right? For instance, well, you write formally, okay, you have to introduce like a small delta. This will come later. You can think about delta equal to 0 now. So you write it like formally this way, so you introduce two parameters, two operators, T lambda and R lambda. And actually by an application of some oscillatory integral to Hormander-Einstein, you get all this boundedness property of the T lambda and R lambda. Okay. So at the end of the game, right, if you adjust everything, you have, because you have constructed, if you want, like, there should be a negative minus 1 here. You have constructed, if you want, like a reproducing kernel, right? A reproducing formula for your eigenfunction, right? Or quasi-eigenfunction. Okay. So one tool that you want us to use when one deals with this type of estimate are like the Koenig-Ruiz-Zog uniform Sobolev estimates. Okay, this is one of the tools. and in Rn, and in the case of manifolds, one can use the analog estimates by Dos Santos, Ferreira, Koenig, and Salo. Okay, so let me kind of sum up what I know now. So let me write. Okay, let me write here. What I know now is that, like, if I am n larger than 4, let's say, I have this quasi-mode estimates, right? I can relate the LP norm of this quasi-eigenfunction to this L2 norm of U, okay, and respect to with like power in the eigen values of this type, sigma p minus 1. And the thing is that whenever v is 0, the argument is pretty clear, is that I basically construct a reproducing formula for u, and I apply some Ormander Hadamard parametrics and some Stein oscillatory integral together with the uniform Sobolev estimate. So as I was saying, like in Rn, like if you use the multiplication operator scales the same way as the Laplacian. So provided this v is in ln over 2. But the thing is that if you are just in ln over 2, even with a small ln over 2 norm, the method that I derived before cannot be used, at least like directly. And because basically I'm using like very heavily, if I wanted to put like a potential, I would be using heavily the smoothness of the potential itself, right? At least to construct like a parametrics, and also to derive actually like Sobolev estimate and so on. But for example, if n is equal to 2 and 3, if I take this critical space, right? So this space is not in L2, and then in particular, smooth function might not be dense in the Sobolev space for the graph norm of HV if V is not in L2. Even like HV, so my Schrodinger operator can be symmetric but not self-adjoint, and even like there are unbounded eigenfunctions for potentials in ln1. So this remedy for the bad cases is putting the potential in the Kato class and using, or because like there are several arguments, a duality argument. So even if like this space is nice, this scale invariant space is nice for dimension at least 4, for some p's, in low dimension, it's not convenient. Okay, it's even like a kind of a bad space. Okay. So let me explain how to how to derive this this crucial, because the whole thing is in this estimate here, like an analog in small dimension. So an easy interpolation argument and trivial bound, L2 bound, implies that one can have this for between 2 and the critical value, and the critical value is this one. Okay, so one needs to prove everything for p between this critical value and this 2n over n minus 4. So let's fix like a small delta, and let's take like a connection of point with maximal delta separation. okay, and a number like of the size like delta to the power negative n. And let's cover our compact manifold. Okay, so with this ball, so it's easy to see that you have this type of estimate, and provided like delta separation is small enough, this constant here is independent of delta. But since you have V in this Kato class, in this scale invariant LP space, you can always choose delta so that this thing is small than 1/2, let's say. Well, then let me write. Let me put U equal to these operators, like these formal operators that I introduced before, right? So imagine that T lambda is actually like the inverse of this operator, right? And then I do like the very fancy trick of adding and subtracting, okay? Because if I use this, right, and if I come back to my V here, if I put my V here, well, if I add and subtract, I just have that. Right? But now, what can I do? Well, if I use the previous estimates that I have on my oscillator integrals T lambda and R lambda, right? It's which are both local and non-local operators. Well, if I use that, I have automatically this, and then the thing on a ball of radius Bj comes out of a trivial Hilbert inequality. Okay. So if you combine this, the Hilbert inequality with this inequality, and you sum up everything, right? Using the smallness assumption because V is in ln over 2, well, then you have like the quasi-estimate, that quasi-mode estimate that you want, right? Well, then you see like this is like a very cheap way. This is like a very easy way out of the solved estimate to get, by the solved estimate, I mean V identically 0 or V smooth enough, okay? To have like the estimate that I want for a potential which is singular. Well, then what do I do for low estimates? Low dimensions. Well, for the low dimensions, I know from what I said before that using Kato classes, actually everything is well explained in the bulletin of the AMS of a paper by Barry Simon. If I use the Kato classes, I have eternal bounds. And I mean, good eternal bounds like of Liao type, if you want, and then actually using a kind of duality argument, but actually you can also like do it like differently. Actually, you get like the remaining dimensions. Okay. So it's been known since the work of several people who are probably in the audience, that if you have eigenfunction estimates, so this type of estimate, where is that? Okay, and even if you have like a quasi-mode estimates, you can actually derive like a whole wealth of theorems in harmonic analysis. Particularly, you can derive Ormander type multiplier theorems so functions of this, by multiplier theorem, I mean a function of this operator or square root of this operator. And you can derive also in a kind of straightforward way some Strickhart's estimates. Okay, and here notice that this exponent is exactly the Strickhart's exponent, I mean the original Strickhart's exponent in the Strickhart's paper. So if you take like a compact manifold of dimension at least 2, and you take like all of, I mean, once again, my potential in Ln over 2n in the Kato class, okay? Then if you look at this homogeneous initial value problem, right, for the wave operator associated to the Schrodinger operator, then you can derive this LP in time, LPC in space and time. Of course, like since you are on a compact manifold, the time is like it's a local estimate in time, and you get that automatically. Actually, this is like almost like a direct consequence, pretty straightforward consequence of the Eigenfunction estimates. So you could ask, well, what happens if I'm in Rn, for example, and instead of being on a manifold? Well, then, at least like a first step, what we need to prove, to assume additionally, to have this type of estimate and to have like a global one, is that the V in Ln over 2 norm is small enough. Actually, one can remove it, but one has to work much more. Okay, and under like some non-degeneracy assumption of the operator, in the sense that 0 is not in the spectrum. So now one could ask, well, okay, so it seems to be pretty. Now it seems to be like almost pretty obvious, okay, how to get this type of estimate, because this one, if you want, because basically it's Hölder plus the SOG's estimates. Well, it's a little bit, one has to be a little bit more careful, because it's not as easy as Hölder plus the SOG estimate. I mean, it seems to be like the way I wrote it here. And, but actually, the crucial point is writing actually reproducing formula of this type. Well, now, what's happening when I try to consider like other types, instead of looking at a second order operator, like a Laplace-Beltrami, let me look as powers between 0 and 2 of the Laplace-Beltrami. Okay, so this, of course, like you are in a compact manifold, right? Closed manifold, so it's easy to define the powers by, actually you can even define with complex powers by means of functional calculus. And this type of operator appears, for example, in quantum mechanics, like if one looks at all papers of Lieb and Dobertschis and related to the stability of matter and so on. So in particular, they look at at the square root of G plus the potential. Well, if you want to get like eigenfunction estimates for this type of operator, one will need also to introduce like a Kato class K alpha, which is pretty well defined, understood. And then indeed, in this case, one get, okay, so here I wrote it for another quantity, which is like the spectral projection operator on the frequencies lambda, lambda plus 1. And one gets this type of estimate. Okay, so if you consider an eigenfunction of this operator, let me take like here the power alpha by analogy, because before my operator was for alpha equal to 2, and I put lambda square here. Then you have this type of eigenfunction estimate. Okay, and sigma p here is as before. So the thing is that here alpha is between these two numbers. So it might be one could think that it's like almost like after all, like the powers of the Laplacian are well defined, right? I mean, it's pretty easy to define them in a bifunctional calculus, right? But actually, like there is a problem here, is that using an analog of this reproducing formula here. And the problem is solved by using a quite complicated formula one can find in the book, because like, as I was like mentioning, this T lambda basically is, that I was writing before, is basically the inverse of this operator up to an arrow. Okay, so it's an Hadamard parametrics. So in this case, when you take like a you might consider function, or at least here powers of the Laplace-Beltrami, it's not clear how to derive this type of oscillatory integral. I mean, like this type of inverse operator. Okay, here I have like a local integral, and here I have a non-local one. Local, I mean like it's for t close to 0. Rho is just a cutoff function. Well, fortunately, there is this formula that if you take like one can find in the books, if you take like the inverse of this thing, okay, of my operator, okay, which is like the one I want for some z, some special z, then I can write it as this nice integral, here, plus this kind of nasty one. But both, both involve the same operator here. Here, this is clear, right? And here, you have again the resolvent at level gamma of the Laplace-Beltrami, right? So basically, now one could think, okay, I know that this type of operator can be written as a local one and a non-local one, for which I have good mapping properties using like Ormander type estimates. Well, then I could apply here, except that of course here one has to take into account like one is integrating over the whole resolvent set. It's complex. So the thing is that I'm not aware, but maybe it exists, but I'm not aware of formulas which are as precise as this one when you take other things than powers, at least real powers, and here between 0 and 2 actually, of the Laplace-Beltrami operator. So let me mention like a last, let me mention a consequence of these estimates for the case alpha equal to 1, because it's of interest in the recent literature in spectral geometry. Actually, this estimate automatically give estimate for Steklov eigenfunctions. And why is so? Well, it's some sort of intrinsic version of the Steklov eigenfunction. So let's take like a manifold, compact manifold with boundary. And let's look at the Steklov problem. I mean, a generalized Steklov problem, which is I put an harmonic function inside, and on the boundary, I put like a Robin type condition, but with a potential. So du d nu plus vu and equal to lambda square u, or lambda u. Okay, so I have an harmonic function in my manifold, and on the boundary I have like a Robin type or generalized Robin type boundary condition, which would be du d nu plus vu equal to lambda u. So if v equal to 0, this problem, okay, the spectral problem is known as the Steklov problem, okay? Well, now I have like perturbed the Neumann derivative by my potential v, okay? So du d nu plus vu equal to lambda u. And v, I know that, so first, eigenfunction estimates work for, I mean, can be derived for the Steklov problem. And this is a consequence of some previous estimates by Sorg and Sire, and also like a little bit of pseudo-differential calculus, and it's been derived, for instance, by juillet. And why this is almost equivalent up to a smoothing operator to this problem, because du d nu, if you take like the directly to Neumann operator on a smooth manifold with smooth boundary, du d nu is at first at leading order square root of the Laplacian of the Laplace-Beltrami on the boundary plus a smoothing operator, okay? So basically the smoothing operator will not dictate, of course, will not like dictate the regularity because it's smoothing. And so basically this problem gives you automatically in the case of, I mean, this result gives you automatically in the case V being singular, okay, so V being like L n's over alpha when alpha is equal to 1, okay, so Ln, it gives you automatically eigenfunction estimates, okay, for the generalized version of the Steklov problem, du d nu plus, I mean, harmonic inside, du d nu plus vu equal to lambda u. Right? So I don't, maybe it's, I think that in some papers, this is called Steklov-Robin, I think, or something like that. Okay. And somehow like it gives even like more information because somehow because one has like a very precise, so this is, if you want, the leading resolvent of if you want your directly to Neumann operator, and it gives you a very quite precise estimate of this. So one, of course, one could think, okay, like if I have like this type of estimate, precise estimate for this generalized version of the Steklov problem, can one say some things about like unique continuation on the boundary and so on? And of course, like it opens like this type of interesting thing. So, so let me mention like some open question to finish. I went very fast. So there are several things that one could look at. The first is a case of domains, okay, or manifolds with boundary with this type of potential. I think that people in mathematical physics are even interested by more singular problems when, for example, the potential is no longer not even in ln over 2, but is like a Dirac mass or a measure or something. Okay, of course, like when you have like complex valued, for example, potentials, I mean, the theory, I mean, is starts being substantially different from the case of real value. Okay, and one can ask, like, is there like a similar estimate on when you try to go below even this type of singularity? So for example, either singularity for the potential, you take a smooth manifold, but you take your potential to be a random measure on the manifold, or even if you look at, you take like the same type of potential that I looked at, or even like a smooth one, but now you have like singular manifolds. And in particular, manifold with conical singularity. So in the case of identically zero potentials, right, or very smooth potential, there are some results when you have manifold with conical singularity for some type of conical singularities. But in general, if you look like higher dimensional singularities, edge type singularities, for example, S1 is in S3, then as far as I know, there is no result about like even SOG's estimate. There is like a paper by Hart-Smith about like that one can go all the way to C11 metrics to recover the SOG's estimate, but actually if one takes like other type of singularities, what remains, this I don't know, and how the singularity is affecting actually the behavior of the eigenfunctions, for example, their LP estimate. Okay, so I think I'm gonna stop here. Thank you very much.
Thank you very much for this talk. And we have plenty of time for questions. If you have a question, please just unmute yourself and go ahead.
I have some questions. Yannick, can you hear me?
Yeah, I do hear you still.
I guess in your talk, you assumed that M is compact. Am I right?
Yeah, yeah.
But, you know, in quantum mechanics, there are many interesting singular potentials that arise in Rn. Of course, then you can't really study, or you probably don't want to study global LP norms, but you can study them locally near the singularities of the potential, for example. I mean, you have estimates, but, you know, obvious question is, you know, where are the LP norms concentrated, right? Are they near the singular points of the potential?
Yeah, yeah.
You know, a funny example, I was just looking it up, is in the case of hydrogen atom, where you have a 1/r potential. Of course, you have issues because you have a continuous as well as discrete spectrum, but we can look at the discrete spectral subspace. So I looked it up, and all of the eigenfunctions are analytic, actually, at r equals 0, where the singularity is.
Oh, okay, okay. So 1/r, you said, right?
Yeah, this is the Coulomb Hamiltonian.
The Coulombian potential, yes.
So they're all, you know, well, so first of all, curiously, I guess, I don't know if that's curious or not, but they all are analytic near the singularity of the potential. And they don't seem like they're big there either.
they are
So
not, oh, you mean they are not like concentrating?
it does not seem that way to me. You can look them up, but they're just given by certain like Laguerre polynomials times e to the minus r over something, and
Okay.
multiplied by a power of r, which is positive. So I think an interesting question. I mean, let me put it this way: it's partly a question and partly a comment. Do you have interesting examples where you see exactly how singularities of the potential change LP estimates and eigenfunctions? Good examples of what you're doing. And secondly, sort of, there seems to me like a whole natural area of questions is to really study the eigenfunctions locally nearby the singular set and try to figure out if the reasons why LP norms might be large are due to the singularities, or exactly where are they large and how it's related to the singularities.
Yeah. This is what I was mentioning at the end. I think it's very interesting to look at this problem. Yeah. At the moment, the only example I have, or like of badly behaved eigenfunction is like you can very easily cook up like an unbounded eigenfunction for potential which is not in dimension 2, which is not in the class that I consider. But I guess like it's not like that. I mean, I don't know. I mean, it doesn't seem to be like answering really like your question. If it's, I don't think it's an interesting thing. It would be much more interesting to see like how, as you say, like the singularity of the potential is influencing the concentration of the eigenfunction. But maybe one way to look at it is like, trying to see like the singularity as a manifold with boundary, right?
Yeah, neighborhood, just local estimates.
Local
LP. Actually, it just occurred to me something. You see, because of the sign of the potential, Coulomb, the Coulomb potential is repulsive.
Yeah.
And might push eigenfunction mass away from the singularity. But if you switch the sign of the Coulomb potential to make it attractive, then maybe the eigenfunctions respond by being big at the singularity.
Can I interrupt for a second? So for hydrogen, for the ordinary attractive hydrogen, the eigenfunction is Lipschitz and only Lipschitz. And this is called in quantum chemistry, that's called the Kato-Cusp condition. The first eigenfunction.
That's what he's talking about. It's a 1 over R potential, but
it's e to the minus.
It's actually repulsive, right? And we're talking about electron going around the nucleus, so it's attractive, yeah.
Attractive, and it's e to the minus absolute value of x. That's the ground state. It's exactly that. Which
yeah,
just
look
so what you
momentum times the Laguerre function of R, e to the minus r, and so forth. None of them have singularities at the origin.
The Laguerre polynomial is just a 1. The point is that the Laguerre polynomial is multiplied by e to the minus r. And the e to the minus r
we're talking about the local singularity at r equals 0.
Yes, exactly. And it's e to the minus, the function e to the minus r is...
Yeah, none of them have... Oh, I see what you mean. Well, yeah, that's yeah, you're right. I mean, it's not blowing up in any sense. It's just that it's not smooth there.
Right. Mm-hmm. Yes, right.
So
the derivative has a jump.
What you say, Rupert, is like it depends a lot on the sign, right?
Yeah, that's another thing. Exactly. Yes. Oh, that's also what Steve said. Yes.
Yeah.
Right. So
if it's
if it is repulsive, then the wave function wants to be small there. Yeah, that was just a short remark. I didn't want to interrupt anything.
No problem, thank you. There's also a comment in the chat by Victor Ivry who says that for hydrogen, the standard eigenfunctions, there could be combinations of them with the same energy that could behave differently. I cannot.
Well, no, okay, so they have the multiplicity of the eigenspaces n squared for the eigenvalue minus 1 over n squared. So you can, just like in all cases where you have these huge multiplicities, if you look just at, the spectral projection and you fix one slot of it, then on the diagonal, it's going to have dimension. It's going to basically be of the size of the dimension. So you're going to, those things, of course, for standard reason, just like on a round sphere, they optimize sup norm bounds or LP norm bounds for large values of P, right?
So thank you for this question / comment. Are there any other questions, comments from the audience? I have a very simple one myself. I would like to know if the constants that you wrote CV that appears everywhere, how do they depend on the geometry of the manifold?
Okay, so when you do everything is start being no, they don't depend, like for compact manifold, they don't depend. I don't know how they depend precisely on the geometry of the manifold. When you start computing the Hadamard parametrics, of course, like you are taking coordinates and blah, 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 and one has to be careful. In particular, if you have like singularities, or I shouldn't mention that I did, all of this has been done I mean, like what I described worked for compact manifold, but one can also derive some result, like for at least the spectral projectors, okay, on the continuous spectrum, when you have like other types of manifold, like the hyperbolic space, or asymptotically hyperbolic, or asymptotically Euclidean, and so on. At least like spectral bounds, right? By spectral, so you take the projector, define like as a multiplier on some piece of the continuous spectrum. But I don't know exactly. I mean, like it's not clear to me how they define how do they I mean, how the constant change with the manifold, with the geometry of the manifold. But let me mention that even in the case of the SOG estimate, so the classical estimate, one can improve them when one can get better estimate when one assumes, for example, negative curvature. So, and the reason why is that, like, well, I mean, like, there are some, in negative curvature, one can use like some structural theorem by Bérard, and then one can get like better estimates than the ones that I stated here, which are like sharp in some kind of generic way. But of course, like I don't know how they depend on the geometry of the constant, unless like maybe like, of course, like if you have p equal to infinity, right, if you take the sup norm, then of course this is basically related to the Veil law, and in this case one have like more results, right, more precise results as far as the dependencies are concerned.
Thank you. Does anyone else wants to say something?
Yes, please, about one query for Yannick on the potential. It should be at least locally bounded and upper bounded, something like this, or no?
No. The only is like ln over 2, and that's it.
But we are sure that we get a self-adjoint operator, or no?
Yes. It's so in dimension larger than 4, right? Or we are in even like in L2 in particular. So then by it's going to be a self-adjoint operator with a smooth function in the domain and so on.
Okay.
The problem is like below in n equal to 2 and n equal to 3. In this case, indeed there are some functional analytic issues, and that's why one has to assume that you are in the Kato class. But in any case, if you want to have like the whole range, okay, then one of p's, Okay, then one has to assume that you are in ln over 2 and in the Kato class, and no, it's not a trivial assumption. I mean, there are like, you have to be in the intersection in the way that these spaces are not embedded in one into the other, right?
Okay, thank you. Thank you, Yannick.
Thank you. Anyone else? If not, let's thank Yannick again for this talk. Thank you very much.
Thank you.
Thank you, Yannick.
And we will reconvene next week for the last talk of this session with a talk by Victor Ivry, who will speak about pointwise spectral asymptotics out of the diagonal. So this is next week, July 26th, same time. Meanwhile, have a safe week, and everybody take care. Thank you.
Bye-bye. Thank you.
Yeah, thank you very much.